Hello and welcome to the third lecture of software architecture. We are still in the introduction phase. So in this lecture, I will talk about architecture styles and architecture views. So in the previous lecture, we discussed about what is architecture, what is not an architecture. And now we are going into little bit details. We are talking about architecture styles and views. These are possibly the most fundamental part to understand, describe architecture. So let's start with architecture style. So the word architecture style was first proposed by Shaw and Garland. And if you recall in the previous lecture, Shaw and Garland are one of the pioneers actually. These two people are one of the pioneers in software architecture. Basically, they had been instrumental in defining software architecture, and they had been instrumental in even creating architecture description languages, and they use the term called architecture styles. So style is basically synonymous to architecture pattern. So in other words, style and pattern are more or less the same. They mean the same thing today. So what exactly is a style? It is basically a set of element types. And by element types, it means that what the element does. Here element means a unit of computation essentially, or a module. So essentially a set of element types means what the element does. Example is that you could have a element which is basically storing the data. You could have another element which could compute a linear regression function which will be used by some other modules. So this is an example of an element. And I would like to highlight again that for the module like linear regression function computation module, we are not describing how the linear regression function is computed inside the module. So the detail part is again a part of detailed design. So at the architecture level, it is just mentioned that it computes linear regression function and it can be used by somebody else. That's a set of element types. A set of interaction types. So these elements, if you want to treat them as boxes, then interactions become lines. So a set of interaction types means that how these elements are interacting with each other. So if you are drawing a line between two elements, then that indicates an interaction. You have to describe what kind of interaction it is. Is it a data flow? Is it a call graph? If it is a call, then what kind of call it is? Is it like function call? Is it module 1 is calling module B using some functions of module B? Or is it like they are exchanging data through a publish and subscribe kind of a mechanism? Maybe that there is a message bus, and these two elements are interacting with each other by exchanging messages. So nobody is calling function calls. There is no function call happening. It could be publish, subscribe, and you can add any different types of interactions. So fundamentally it's very simple. A set of elements, set of interactions, and they have their types. Then there is something called topology that indicates the interaction and interaction types. Topology is nothing but the way these elements are connected with each other. These elements have their types, in these interactions have their types, so then the whole graph is essentially the topology. Then you have to add something called constraint that can describe what all are allowed, what are not allowed. And this is also called, as I said earlier, architectural pattern. So a style is essentially It comprises of a set of elements, interactions, their types, and the topology. We shall cover some of these patterns in detail, as I said, in the subsequent lectures. Then the next important part is architecture views and architecture structure. If you remember, we talked about architecture structure and architecture behavior. We are now focusing on architecture structure. So, since the architecture serves as a vehicle for communication among the stakeholders, it's a blueprint, and each stakeholder is interested about different aspects of the system. If you recall, we showed an example where there were stakeholders from all different parts of an organization. Like, for example, one stakeholder was a CTO or chief technologist. Another stakeholder could be a developer. Another stakeholder could be let us say deployment engineer. Another stakeholder could be a database guy. Now each of them are interested about different aspects of the system. It is obvious that a developer is not interested about what is the overall policy that you have in terms of choosing the technology, or all that developer needs to know is that are you using C++ or you are using Java or you are using OpenStack, and that's all. But the database guy is interested about more of data storing, retrieval, safety, archival, not interested about other things. So likewise, their interests are all different, and therefore it is really complex to describe, understand, and even analyze the architecture using one common vocabulary for all stakeholders, because they all talk in different languages, different terminologies. Therefore it is really complex, and it is not even advisable to basically have one common vocabulary. Therefore it must be described in a multi-dimensional manner. So any entity that is complex has multiple dimensions. It is not really advisable to reduce those dimensions to a single dimension just for the sake of making it simple. A very unrelated but maybe a relevant example in this point, which can help you understand what I'm talking about, is about, in general physics we talk about speed and the velocity, where speed is a scalar quantity having just one dimension, which is just a number, which is just a value, whereas velocity is not a value but also it has a direction, so it's two-dimensional entity. So it is not really advisable to just eliminate one other dimension or somehow combine that dimension and then make it a single dimensional entity. If it is a two-dimensional, it has to be represented in a two-dimensional manner. Likewise, in software architecture, it needs to be described in a multi-dimensional manner. So each dimension is essentially called a view. So, and this is what is called a view-based approach. Each view should represent certain architectural aspect of a system created specifically for one or more stakeholders. So this is very important, that if you have identified a set of stakeholders, ideally you should group a set of stakeholders and then create a view for them. And architecture should consist of a set of views. All the views combined together forms the consistent whole, meaning that when you consider all the views together and link them, then it becomes the complete software architecture. So a structure is essentially an underlying part of a view, essentially a set of elements and their properties. And basically a view is created using these elements and their interrelationships. We will talk about a view and a structure later on in detail, but here I would like to clarify it. It may sound a bit complex. Here, when I'm talking about a view, it is As I said, it represents certain architectural aspects of a system. Now question is that how do you represent it? Okay, here I'm just talking about each view represents, but question is how do you do it? In order to really describe a view, you need a structure, which is the underlying part of the view. Essentially, it is basically a set of elements. So, and the elements are the elements that I explained in the previous slide. Elements are essentially a set of computing units or units of functionality. So a view corresponding to a structure is created by using these elements and their interrelationships. That's very simply put. It's more of a structure is okay. So we can take another example. For if you are drawing a particular, let's say, schematic diagram in any GUI development tool. So in that tool, what you can find is on your left hand side there is basically a set of tool sets or palettes where you have boxes, ellipses, squares, and so lines and so on. And on your right hand side typically you would have a big canvas, and you can basically drag and drop different boxes, draw lines. Okay, so on whatever you see on your left hand side, if you are using, let us say, Microsoft Visio diagram, then suppose you want to draw a network diagram, and then you can have a set of toolboxes having different types of icons representing different network elements. If you want to draw a house, then you can have a palette of different atomic elements that represents different parts of house, and then you can pick and choose, drag, draw lines to actually compose your house. So structure means essentially those set of tools like boxes, lines, ellipses, and so on, and certain properties, what can be done with those boxes and lines. And a view is essentially the one that you create using those elements. So that's what it means. In this context, it is important to understand what is called a reference model and a reference architecture. So a reference model essentially decomposes the functionality into a set of smaller units. It describes how they interact with each other and how they share the data, and these units cooperatively implement the total functionality. That's what is called the reference model. And the reference architecture is basically created from a reference model, a concrete set of software elements mapped to the units of the reference model that implement the functionality. And typically a reference model can be thought of as a pattern of some sort, and a reference architecture is an example solution using that set of reference models. So we have reference model, we have architecture patterns, we have reference architecture, and we have software architecture. Now reference model per se is not an architecture. It is more abstract, and it belongs to a particular domain. And architectural pattern is, so far, whatever we have learned or whatever we are going to learn in this course. And if you also look at different other materials about architectural patterns, they primarily deal with non-functional attributes. They are there to address certain non-functional requirements. So they are not architecture by itself. So reference model is not an architecture. Architectural pattern is also not an architecture, but you can combine the reference model and architectural pattern. You can use these two to actually form a reference architecture. So if you are to implement, let us say, architecture, or suppose you want to build a mobile commerce platform. So you will find an example of such a reference architecture, that what are the essential components of a mobile commerce application. So that reference architecture is really not a software architecture by itself. It is nothing but a set of elements, their interactions, and those elements basically would describe what are the typical functionalities. But it will really not address all the quality of service concerns. But it will tell you that what are the essential components that are required. In that sense, the Android operating system diagram that I have shown, it is, you can think that to be a kind of reference architecture. Well, in the reference architecture, you won't need to add few more descriptions there, but that picture essentially shows that what are the essential elements that are required to build a mobile operating system platform. Similarly, to build a mobile e-commerce platform or mobile commerce platform, you could build a reference architecture. But software architecture is essentially created from a reference architecture. That's a specific instance of reference architecture. There you instantiate each element with real modules that are going to be implemented, and you address a lot of other concerns. You add a lot more details, and that makes it a software architecture. So it is basically an actual software system that is derived from the from the requirement. So this one is essentially created from the requirement. Can we pause?
Yes, you can.
I wanted to just use this marker, but it goofed it up.
You have to choose the editing section from there.
Okay. So if I hover the mouse in the video, does a mouse hovering comes?
Yes.
Okay. So this particular slide is bad. I mean, till this point it was okay.
Yeah, you can start from this slide only. You can redo this slide.
Okay, let me just see how many are there. Till 4 is fine.
Yeah, it's fine.
Shall I start?
Yeah, you can continue.
So we are talking about interrelationships. In the previous slide, we talked about reference models, and we talked about reference architecture. Now, note that the reference model and reference architecture are not architecture by itself. In this diagram, what I'm showing is there is a reference model, there is an architectural pattern, you have got reference architecture, and you have got software architecture. Now, the reference model and the reference architecture are essentially examples, best possible scenarios, and things like good practices. So these are all kind of captured in both reference model and reference architecture. Architectural pattern is again a solution, but if you look at it, architectural pattern is dealing with more of non-functional requirements. However, the reference model and reference architecture deals with the functional aspects. So architectural patterns, whatever that you are going to learn in this course, and if you also look at other sources of other patterns that are not covered. In fact, as I said, there are many architecture patterns, there are many design patterns today. So most of them, or in fact all of them rather, they all deal with non-functional requirements and how to address certain concerns and certain problems. Reference model is about building a system for a specific functional domain. Example is that if you look at the example of Android operating system that I have shown, that picture, you can roughly say that that's reference architecture. So those modules essentially describe what are the functionalities that need to be there, but it does not address any other aspects of it, like performance, like memory footprint reduction, like power consumption and optimization, like speed, like reliability. It doesn't talk about that. It just shows what are the functional elements that are required. Therefore, it can be a good reference architecture for the mobile operating system platform. You could also have a reference architecture for, let us say, mobile commerce platform, but they are not architecture by itself. So a reference model is essentially, as I said, a set of elements and their types and the way they interact, but not necessarily about different non-functional attributes. So it is really not an architecture by itself. Architectural patterns also is not an architecture. Both of them are used to form our reference architecture. Now, if some of you are familiar with Java development and J2EE platform, it actually gives a reference architecture of a typical J2EE application. So that reference application and its architecture is basically the reference architecture. Now, if you really look at that example coming from Oracle, earlier it used to come from Sun. So that whole example is, as I said, it's a reference implementation. So the whole thing works. It runs. It has got a design implementation. It has got its architecture also. So the architecture part of it can be treated as a reference architecture. But these are truly not software architecture because it is not specific to a particular problem statement. It is just an example to highlight certain aspects of it. Like a mobile commerce platform is really not a software architecture. It's just a reference architecture. But if Airtel or Vodafone or any other company, they basically uses this reference architecture and builds their own platform, then it becomes a software architecture. So in a sense, software architecture is an instance of reference architecture. Actual software system blueprint that is derived from the requirement is the software architecture. It contains design decisions. Now, reference architecture really does not have any design decisions taken. The design decisions say that why a particular module was chosen, why there is an interaction like that, and what are the compromises that have been taken for what is the purpose. So these are all the design decisions. It describes how it is deployed. In reference architecture, there is no description of how it is deployed. Most importantly, it addresses the quality of service concerns that reference architecture will not do. So I spent quite a bit of time in basically explaining software architecture as well as the reference architecture, because oftentimes you will find a lot of such reference architectures in the internet, and many of them are really useful if you want to build applications on your own. But when you get certain useful contents from the internet, you better know that what you are using. Is it a model that you're using, or is it a reference architecture you're using? Which is why I spend time in basically explaining this reference architecture and software architecture. So there are different benefits of software architecture. I'm sure by now you are at least to an extent convinced that architecture is required. So let us look at what are the benefits that one can get. The first one is really important one, and it may sound trivial or it may sound simple, but trust me, this particular benefit is something that makes a huge difference in a large corporation. Every stakeholder understands unambiguously what the blueprint is. So that means there is a complete standardization of the approach, vocabulary and the output. That means everybody understands what the other group is doing, and there is a common language for communication across different stakeholders. That definitely helps in streamlining the work assignments. So if there are multiple teams, there quite a bit of time is spent in basically streamlining the work assignment, and sometimes that becomes too much to really to really implement a particular piece of software. The whole work assignment, whole controlling aspects of who is doing what or what time they're finishing, is there a misunderstanding of what is expected. So all these things are a huge overhead in terms of with respect to implementing a software, and oftentimes the project teams really do not estimate such overheads. They don't even consider that. They assume that everything will go on fine, and they just compute the estimates based on the complexity of the software, the function points and so on. But the streamlining part is a real challenge, and that's never or hardly considered. So architecture actually helps in streamlining things, and it can avoid information loss, it can avoid such ambiguity, and it can enforce the traceability, that what are the requirements that were considered, what are not considered, and if they're considered, where it has been considered. Design decisions can be made early. This is a huge benefit, because if those design decisions are not made early, and if they are not evaluated and corrected later on, oftentimes there are problems and there are rework. So it is, and at the architecture level, because it is at a high level, it is quicker to evaluate these decisions and actually correct it rather than discovering it late. As I said earlier, it takes 10 to 100 times more effort if it is discovered during testing or during deployment. It can be a disaster. Early analysis of quality of service and evaluation of architecture is possible if one creates a software architecture properly. Early analysis of meeting the quality requirements and different compromises are also possible to analyze, because not every quality aspects can be really met. Sometimes they contradict each other. So one needs to really assess that what are the contradictory requirements and how one has to choose one versus the other. So, and the best place to analyze and decide such kind of contradictory requirement is at the level of software architecture. It really shouldn't be done at a later stage. It should be done only at the architecture stage. Now, important aspects of the software, like the example that I gave, that one need to download, or one need to acquire 1 terabyte of data per day. Is it really possible? If so, how one can do it? So these things must be addressed at the architecture level. So, and that requires prototyping. So early prototyping of important aspects can be done if the software architecture is actually considered and implemented properly. In fact, that helps in more accurate cost and schedule estimation. Without the software architecture, it is simply not possible to have an accurate cost and schedule. And as I said earlier, streamlining of work assignments becomes a major problem that can actually make all this cost and schedule estimates to go haywire. Things become wrong, and in fact it becomes a major overrun. So architecture is important, otherwise this accurate estimation is not possible. It also improves the speed of development. In fact, if in a large organization, if reuse is to be promoted, and reuse is a buzzword, or reuse is a mantra that many corporations use, they really want to reuse the artifacts generated by one project team in another. So essentially, that's possible only if one does software architecture properly. It helps in building a large product line by sharing the common architecture, because everybody is speaking in the same language, same vocabulary. Reuse is possible from one implementation to another, and based on the architecture, one can quickly decide whether one needs to build or use external component, or needs to use internal components. So such decisions can be made really quick. Then tools that can automate part of development and testing, that also can be used. In fact, there are tools which call model driven design, model driven development, which can generate code, or at least a part of the code from the high level design, which can be created out from the architecture. Certain tools can be used to automate the testing also. So in a sense, architecture helps in using those tools. In this particular course, we will learn 3 structures. Structures, again, there are structures and views that I have talked about. Views are the ways you describe structures, are the elements that helps you in describing. So we are going to learn 3 different structures. One is called the module structure, in which the main concern is how is a system to be structured as a set of code units or modules. That's the main purpose of module structure. You will describe a module structure using a certain elements. The whole purpose is to basically understand how a system is organized as a set of code units. Then the second structure is called component and connector structure. This structure describes how the system is designed or implemented as a set of elements that have a runtime behavior and their interactions. So in this context, a component means an element that has a runtime behavior. In other words, a component could be things like a shared library. A component can be a unit that runs, maybe executable, maybe a web service. So these are all kind of components, and these interactions are the way these elements exchange data, exchange control instructions, and so on. So what are the major executing components and how do they interact is basically the whole purpose of component and connector. The third one is called allocation structure. The allocation structure says that how is the system is related to non-software structures. For example, how is this software system is connected to environments like CPU, cluster of CPU, etc. So using allocation structure, you can describe its deployment, how the system is going to be deployed, on what machines, how many machines, how the data is going to be stored in different file systems, how the communication is actually happening through the networks. We talked about interactions, which are connectors, but how are those things going to happen in reality is through network or function call, etc. So these are a part of allocation structure. Then development teams, how the system is going to be built by a development team or a set of development teams. So how the modules would be assigned to different groups for implementation. So that's also about allocation structure. So we're going to conclude this lecture, and we conclude by basically showing different parts of the software architecture in bits and pieces. By different parts, I mean that software architecture is something that has been in existence for a long time, from early 80s, and people had been working on software architecture for a long time, both researchers as well as practitioners, and so many softwares have been built. In fact, software has become a part of our life today, and in that process people have touched upon different architectural aspects, and here I just wanted to give a snapshot of all these aspects. For example, people have worked on architecture descriptions, how architecture can be described, and there are tons of work. Standards like ISO, standards like IEEE 1471, then RUP, Rationals 4.4+1 views, ISO's 9126 definition of software quality, architecture modeling languages like UML, architecture description languages which came out of many universities, modeling of behavior using BPML, PatriNet, state charts. There are various patterns, industry specific patterns, different reference architecture examples like IBM e-business architecture patterns, examples like insurance architecture, which is a reference architecture. Example of reference architecture could be HIPAA architecture. Different architecture styles have been proposed. There are various tools that exist today, many open source tools to describe architecture, like Acme XADL. These are all open source university tools. Not many people in the industry use it. IBM's Rational System Architecture is a popular commercial tool. Many quality of service analysis tools exist in bits and pieces. Then architecture methods and analysis tools. These are also are in existence for a long time. For example, queuing models to analyze the performance of a system. Mean value analysis techniques, Markov modeling for availability analysis, formal verification of a software, rule-based systems for applying different architectural heuristics. There are different best practices that are just there as a document. So such kind of things are there in abundance. There are many architecture frameworks and processes that have been proposed, like TOGAF is a well-known process as well as architecture framework, but TOGAF is primarily for enterprise architecture. Then Zachman also have been working on software architecture, but they have all proposed the enterprise architecture of a family of systems, not just one system. But in this course we will only learn architecture for one system, not a family. For that you need to learn what is called enterprise architecture. Then Software Engineering Institute from Carnegie Mellon University have proposed techniques like ATAM or SAAM to basically understand different compromises that one has to make on different software quality attributes. IBM has proposed enterprise architecture standards, C4ISR, US Treasury architecture, the different development processes. They all have proposed, described different frameworks and processes that one need to follow to describe architecture. In this course, we will touch upon UML as architecture modeling, and we will touch upon RUP for the process part. So that's all for this lecture. Thank you.